So the next thing we're going to talk about is kinematics and how to use integration with them. But before that, let's think about how we use derivatives to do kinematics. So kinematics is all about motion, right? And all about sort of displacement. And other than the displacement, what else do we have?
Velocity.
Exactly. And other than velocity, what else do we have?
Acceleration.
Yeah, exactly. And we spent a bit of time talking about the definition of these things and so on. But how do I get velocity from displacement?
First derivative.
Yep. How do I get, and to be clear, derivative with respect to what?
Time.
Yeah. And how do I get acceleration from velocity?
Derive it again.
Yeah. And obviously, you know, if we call this x, then we can call this dx dt, sometimes written as x dot. We can call this the second derivative of x with respect to t, which we call x double dot, or we can call it dv dt. And sometimes you'll see that written as v dot. And then we've also talked all about, you know, how you've got xt graphs, vt graphs, at graphs, and how they relate to each other in terms of concavity, increasing, decreasing, and all those things, which you can go back and look over. That's not going to be our focus on today, though. So you can look that over if you have any trouble, which doesn't sound like you do, which is excellent. We're going to focus on integration. So, I mean, I've written in a separate column here, but if you think about it, if you derive and you get the velocity, and you derive and you get the acceleration, how do you think integration would apply here?
You can integrate acceleration to get velocity.
Yeah. So really, it's just, I mean, I don't really need an extra column. It's just this part. And same thing here. And that's why if you understand what derivatives and integration are, you understand what these things are, then it's really simple. Does that make sense?
Yeah.
Now, remember, what did first derivative represent?
The gradient.
Yeah, and that's why velocity is the gradient of a displacement time graph, right?
Yeah.
And you know, that's why acceleration is this gradient of a velocity time graph. All right, what does integration to represent?
The original graph.
Nope. The integral does not represent the original graph. We talked about it just now as well. If you integrate a function, you get a different function, which is not the original graph. And what would that represent?
We talked about it before.
We talked about it just today. If you integrate fx, what do you get? Basically.
You get capital Fx. Oh, the area under the curve.
Yeah. That's why this might make a bit more sense to you now. I mean, we've talked about it, but now that we've done it, so a displacement time graph let's make this a quadratic. I'll do it this way. I'll deliberately throw in some numbers. Okay. And your velocity time graph might look something like this. And your acceleration time graph might look something like this. And so now, remember you've got your different types of graphs here. And that's why you do need to pay attention to see what type of graph you've got. But we've said before, the gradient of a displacement time graph, what is that?
Velocity.
Exactly. The gradient of a velocity time graph is?
Acceleration.
And the gradient of acceleration time graph is called jerk, which we won't need to care about, but it's basically the next derivative down, all right? What's the relationship between acceleration and displacement?
Concavity.
Correct, because it's a second derivative. So the concavity would represent acceleration. So you can see that in this case, the concavity is up, it's concave up, which is telling us that acceleration is positive.
Yeah.
So now, what do you think the area would represent under acceleration time?
Velocity.
Yeah, or more technically the change in velocity, but yeah, it's ultimately velocity because you need to take the area from somewhere to somewhere. So the area under the curve would represent the
Displacement.
change in displacement. Yeah. And so you can see all the concepts that we've talking about before now basically apply, right?
Mm-hmm.
And so when we did kinematics, we focused on the derivative aspect. So derive displacement get velocity, derive velocity get acceleration. Now all you need to do is just do the reverse. Integrate acceleration to get velocity, integrate displacement to get integrate velocity to get displacement. All right.
Mm-hmm.
Now there is one complication, not very hard to get around. You just need to understand it. So we might do a quick example question here, but there is a slight complication with integration though. So remember when you integrate, what do you always need to do?
Plus a constant.
Exactly. And do you know what the constant is?
No.
Right. So the complication is you need to work out what that constant is.
Oh, okay.
And that's why I've said you must remember to do plus C. Because there is a constant. You can't assume it doesn't exist. In fact, it does exist. So we'll just take a very simple question to show you what I mean here. If we've got some sort of velocity equaling 1 minus 2t, for example, and we're told that the particle is initially two centimeters to the right of O. Do you understand what O means?
Origin.
Yeah. So this basically means origin. And do you know what origin means in this context?
0.
Yeah, x equals 0. So if we're letting x be displacement, it means that's where the displacement is 0. So in other words, diagrammatically, you've got some origin O, and we're saying that the particle starts here. Now, generally, we would assume to the right is positive and to the left is negative. So all that vector stuff basically coming back again. Yeah?
Yeah.
All right, all makes sense so far?
Yeah.
Now, interpret this statement. The particle is initially, what does initially mean?
X equals to 0.
No.
Y equals to 0.
No.
Oh. Well, 2 centimeters.
Initially. All I want the word is the word initially.
Time equals to 0.
Yeah, it means at the start, which means t equals 0. Then 2 centimeters to the right of O. So at t equals 0, what do we know?
X equals to 0.
Exactly. So this is what's called, if you like, an initial condition, or sometimes called a boundary condition, if it's not t equals 0. But basically, it's information the question gives you that you need to keep in mind. So whenever you read a question, you should convert what they're telling you into, at t equals 0, x equals 2, all right?
Mm-hmm.
Then you just basically do this. So question, find the displacement function. So I've got velocity, right?
Yeah. Yeah.
How do I find the displacement function?
You integrate.
And that's it. And this should be pretty easy to integrate. I don't think you'll have too much trouble with that. Is that all I need to do?
2 plus c.
Exactly. E to plus c. Now, how do I work out this c?
Can you sub the point bracket?
That's exactly what you need to do. You now need to sub in your boundary conditions. Because we know that that must be true. So sub t equals 0, x equals 2. In other words, we're saying 2 equals 0 minus 0 squared plus c, which means c is?
2.
Exactly. For this particular question, we need c to equal 2 for it to make sense. And that means x is no longer just t minus t squared plus c, but it is specifically plus 2. And that will be your answer to this question. See, if you left off the plus c, and you would just say x equals t minus t squared, but that's not right. If you accidentally left off a plus c when you integrated it, you've essentially assumed c equals 0, but you can't assume that.
Yeah.
It might equal 0, potentially. Like, there are situations where c equals 0, but you can never actually assume it. You need to figure out if it is 0 or some other number, always. We're no longer just integrating things indefinitely without, we're applying them to a question. You need it to actually fit the question's criteria. Okay. Okay. So now we've got we've worked out v equals 1 minus 2t. We've worked out x equals t minus t squared plus 2. And we remember that at t equals 0, x equals 2. Then the next question is going to ask, find the total distance traveled in the first second. So, any idea how we would do that?
Do you need to use the E equals to ST formula?
No, there's no such formulas, right? I mean, well, there are, but you don't. So basically, here's the thing, right? Remember distance, right? Maybe it would help to sort of draw these curves out so you get a bit of an idea, right? Yeah, you don't have to draw the curves out. I'm just kind of showing you. All right.
Wait, are you drawing a curve? Or
Oh, well, yeah. So that's going to now be it's going to look like this, basically. not to scale, but it's going to look like this. Yeah. So if this is our xt graph, we're going to start at 2, and you can see that it's a little bit annoying because, well, see, we want to work out the distance traveled in the first second, right?
Yeah.
Now, the distance traveled in the first second is, if we're looking at it from the xt graph point of view, you might get to see what's going on here.
Okay.
So can you see that basically this is displacement against time? So we're saying we start at x equals 2, we go up to 2.5, 2.25, and we come back to 2 at 1.
Oh. Okay.
In other words, what this graph is basically saying is that I'm going to go to 2, then I'm at t equals 0. I'm going to go to not to scale, 9/4 at t equals 1/2. And then I'm going to go back. Does that make sense?
We're gonna go back.
Yeah.
Oh yeah.
Okay.
Yeah.
So what many students might have done for this question is they just go, oh, you know what, first second, I'll just sub x equals 1. So they go, okay, if I sub, sorry, not x equals 1, what am I saying? Sub t equals 1. So if we do that, we will find that x equals -1 squared plus 1 plus 2, which is just 2, right?
But that's displacement. Wait.
Yeah, it's exactly, it's displacement. But lots of students would then just go, oh, well, you know, the distance is basically initial displacement minus final minus initial displacement. Like a lot of students would just say that. Final displacement minus initial x, which is 2 minus 2, which is 0. And as I think you're pointing out, that is clearly wrong. And all those things that we talked about, distance and displacement and so forth, now basically come back to haunt you, right? So I said it wasn't useless, right? So you do recognize that clearly if we just stayed at 2 and didn't do anything, then this distance will be 0. But because we can see that it goes from 2 to 2.25 and then back to 2, then actually the distance, if you like, is going to be 1/4 plus 1/4, and so the actual answer is 1/2. This is correct. So I'm attempting to show you that by drawing out this curve here, rather than just subbing in numbers, to see that you're going from 2 to 2.25 and back to 2. So you're basically doing this thing here, all right?
Yeah.
Now, I used x to do this question. Alternatively, I could have used v, and maybe you would find it easier to do v. So let me show you doing it with v, and I'll draw, you know, alternative method. You might find v easier for this particular question, but I guess I just need to show you different ways of doing it. So we know that v equals 1 minus 2t. And if we draw that out, which is probably fairly simple to do, it'll look something along the lines of this. All right, and it keeps going as well. All right, make sense?
Yeah.
Now, remember, what is displacement as far as velocity is concerned?
The integral.
Which is the area, yes?
Yeah.
So can you see here that the green area and the blue area cancel each other out, so to speak? If we're talking about displacement, they would cancel each other out, right?
Yeah.
But because it's distance, they're both positive, you know? This is moving some distance and this is moving some distance, right?
Mm.
So if you like, you can just work out the area. So the distance would equal, you know, the green area plus the blue area, because it's distance. And that would just be Well, half times 1 times a half plus half times 1 times a half just means a half again. Does that make sense?
Yeah.
Good. Any questions with that?
No.
Yeah, so I mean that's basically, I mean obviously there are, you know, more complicated functions than just linear and quadratic. You'll still need to know how to do exponential and log and all those other functions, but basically that's the idea here. And you do need to be very clear about the distinction between displacement, velocity, acceleration, and their, you know, relationships with each other, as well as the difference between distance and displacement, as noted in this question over here. And the other thing you need to worry about, of course, is the difference between speed and velocity. And for all intents and purposes for your questions, basically you can think of speed as equal to the absolute value of velocity.
Mm-hmm.
Does that make sense? Whereas the difference between distance and displacement is more nuanced, and you will have to examine what, you know, you would need to examine what the particle is doing. Does that make sense?
Yeah.
Great. So next week we're going to then basically talk about, you know, applications. So basically find volume. So we didn't really get a chance to do that today, but it's more important to make sure that you've got everything, you know, we've talked about, that you understand.